Hello statistics and welcome back to the video lecture series. Today we're going to be starting chapter 4 and we're going to continue to discuss some topics of probability. Today we're going to start specifically talking about what are called probability distributions. So before we get into probability distributions, we need to talk about what random variables are. So a variable x is a random variable if the numerical value associated with that variable is the outcome of a probability experiment. So the value of a random variable x is determined by chance. So an example of a random variable could be the outcome of rolling a six-sided die. So the outcomes of the random variable x could take on a value of 1, x could take on a value of 2, the variable x could take on a value of 3, 4, 5, or 6. So a random variable x is the one whose numerical value is determined by chance, and it is the outcome, it's associated with the outcomes of a probability experiment. So there are two types of random variables. We have what is called a discrete random variable, where there are a countable or finite number of possible outcomes that can be written in a list. So the example I gave of the six-sided die is an example of a discrete random variable because there are a countable or finite number of possible outcomes. There were only 6 outcomes and we could list them all, 1 through 6, so that is a discrete random variable. Another type of random variable is called a continuous random variable. And continuous random variables, there are an uncountable or infinite number of possible outcomes that cannot be listed. So such as an infinite number of fractions or decimals that just cannot be put into a list because there is an infinite number of them. So instead of representing these random variables in a chart, we're going to represent them as an interval on a number line, such as x can take on a value of anywhere between 0 and 12. So what we're going to do for each of these describes a random variable x, and we're going to determine whether that random variable x is a discrete random variable or a continuous random variable. So for number 1, x is the number of Fortune 500 companies that lost money last year. So remember, discrete random variables have a countable or finite number of outcomes that can be listed. Continuous random variables have an uncountable or infinite number of outcomes that cannot be listed. So even if that list is very large, if you can put the number of outcomes in a list, it is a discrete random variable. So this is the number of Fortune 500 companies that lost money. Well, there's only 500 companies in total, so even if every single one of them lost money, that would still be a list of 500. 500, while a large number, is still a finite number, and it is still, you could still put it in a list, a long list, but you can still put it in a list. So this is an example of a discrete random variable. For number 2, let x represent the volume of gasoline in a 21-gallon tank. So the smallest value that x could take on is 0. The biggest value that x could take on is 21. And it can take on any value in between. So there can be 18 gallons of gas exactly in that tank. There could be exactly 4 gallons of gas in that tank. There could also be 5.25 gallons of gas, or there could be 11.721 gallons of gas. There could be 17.887. So you can see that there are an infinite number of decimals between 0 and 21 that this random variable could take. You can have exactly 12.0001 gallons of gas in that tank, and it is still between 0 and 21. So since x could be any decimal between 0 and 21, you can't count them all. There are an infinite number of decimals between 0 and 21. So because there are an uncountable or infinite number of outcomes, this is a continuous random variable. And instead of just putting them all in a list, we say that x will take on any value between 0 and 21. So this is what is called an interval. For this chapter, we're going to be focusing on discrete probability distributions, and then in chapter 5, we're going to get into some continuous probability distributions. So a discrete probability distribution is a list of each possible value that the random variable can assume listed together with its probability. It is a two-column or two-row table where in one column you have all of the possible outcomes of x, and then in the other column are all of their corresponding probabilities. We're going to be focusing on discrete random variables first, which means there are a finite or countable number of outcomes that can be listed. So in order for a discrete probability distribution to be constructed correctly, it does have to satisfy these two conditions. Each probability that is associated with each value of the discrete random variable must be between 0 and 1. So each individual probability must be some fraction or decimal between 0 and 1. And another property of a discrete probability distribution is that the sum of all of the probabilities is 1. Because remember, all probabilities in a sample space have to add up to 1 or 100%. So all of those probabilities do need to add up to 1. So to construct a discrete probability distribution, you first need to figure out all of the possible outcomes and, if needed, make a frequency distribution. Then what you need to do is, once you figure out all of the possible outcomes for your random variable x, then you need to second find the sum of all of the frequencies. This sum is going to be the denominator of your probability. Then you're going to find the probability of each outcome by dividing its individual frequency over the sum of all the frequencies. You're basically finding relative frequency. So it's an empirical probability. It's going to be the frequency of that outcome divided by the total frequency. And you're going to do this for each individual outcome, no matter how many of them there are. Then once you're done, you just want to check to make sure that you did it correctly. Make sure that each probability is a fraction or decimal between 0 and 1. And check that the sum of all probabilities is 1. Now, I will say that if you're doing a whole lot of rounding, it may not come out to exactly 1. It might be 1.95 or 1.001. That's close enough. If it's close enough to 1, like 1.995 or 1.001, that's fine. If it's too much further than that, you probably did something wrong. So for this first one, let's say that a company tracks the number of sales that new employees make each day during a 150-day probationary period. The results from one employee are shown in this table. So in the left column, we have the number of sales that this person made per day, which is the variable x. And then we have the number of days in which that person made that sale, which is the frequency f. What we're going to do is construct a probability distribution for the random variable x. So the first thing that we need to do is, we already have our list of possible outcomes of x. X could take on the value of 1, 2, 3, 4, or 5. We have the frequencies that this person made each of those sales. So what we need to do is we need to add them all together to find the sum of the frequencies. So the sum of all of these frequencies is 150. And this is going to be the denominator of each of our probabilities. So then we need to find the probability that this person made each of these individual sales. So we're going to be finding 5 probabilities. So I'm at least going to start my frequency distribution. My frequency distribution is going to be a 2-column table. It can be horizontal as well, with x in one row and probability of x in another row. So in one column, I'm going to list all of the possible outcomes of the random variable x, which is going to be the numbers 1 through 5. And then here in the other column, I'm going to list all of their corresponding probabilities. So the first thing I need to do is I need to find the probability that this person on a randomly selected day will make exactly 1 sale. So to find that probability, we're going to take the individual frequency for 1, which was 24, and divide it by 150. And yes, you can leave it like that. It is perfectly okay to leave a probability as a fraction, or you can turn it into a decimal, whichever. So this is the probability that on a randomly selected day, this person made exactly 1 sale. So probability of 1 is 0.16, so I'm going to put that 0.16, that probability, in my probability distribution in the same row as 1. So I have x, which could take on a value of 1, with a 0.16 probability. And then you're going to do that for each of these. So next I'm going to find the probability that this person made 2 sales in a day. So that probability will be 33, the frequency for 2, divided by the total, 150, which as a decimal is approximately 0.22. Then you're going to find the probability that this person made exactly 3 sales on a randomly selected day. So that is going to be the frequency for 3, which is 42, divided by 150, which as a decimal is approximately 0.28. Then you're going to find the probability that on a randomly selected day, this person made exactly 4 sales. So that's going to be the frequency for 4, which is 30, divided by the total, 150. And then that will give you 0.20 exactly. And then to find the last probability, you're just going to find the probability that on a randomly selected day, they made exactly 5 sales, which is the frequency for 5, 21, divided by the total, 150. And as a decimal, that is approximately 0.14. And again, you could leave these as fractions for even more accuracy. Whichever MyMathLab tells you to do, make sure that you do it. So this table right here is our discrete probability distribution. It lists all of the possible values of x together with their corresponding probabilities. Another thing that we're going to be doing in this section is we are going to be verifying that what looks like a discrete probability distribution actually is. So we're going to check to make sure that this discrete probability distribution satisfies each of the conditions to be a discrete probability distribution. So you might remember, and I'm going to go back a few slides, a discrete probability distribution must satisfy 2 conditions. Each individual probability must be some fraction or decimal between 0 and 1, and the sum of all of the probabilities must be equal to 1. So let's take a look at each individual probability, 0.216, 0.432, 0.288, 0.064. All of these are all between 0 and 1. So that we're all set with that. Then we need to check to just make sure that the sum of all the probabilities is actually equal to 1. So if you just add all of these together, you do get 1. So since they're all between 0 and 1 and they all add up to 1, yes, this is a discrete probability distribution. So if we're going to do the same thing for each of these, and remember, if you want to attempt any of these before I do them, just feel free to pause the video and then resume when you are done working. So for this next one, this is an example of a discrete probability distribution that's written in the horizontal format. It doesn't really matter. And we're going to determine whether these two are discrete probability distributions. So looking at this first one, let's look at each individual probability. Each of these is a decimal between 0 and 1, which is good. However, if you were to add up all of the probabilities, if you were to add together 0.28, 0.21, 0.43, and 0.15, you get 1.07, which is beyond that acceptable margin of error. This is a little too high. So since all of the probabilities add up to a number that is bigger than 1, this is not a discrete probability distribution. And looking at the second one, yes, you can write your probability as a fraction. So using 1/2 instead of 0.5 is perfectly acceptable. So we have 1/2, 1/4, 5/4, however. 5/4 is 1 1/4. That's bigger than 1. And this is a negative. Remember, probabilities cannot be negative. So this table has a bunch of problems. We have a probability that's bigger than 1, and we have a probability that's less than 0. So because not all of the probabilities are a number between 0 and 1, this is not a discrete probability distribution. I'm not even going to bother adding up the probabilities because these numbers are not probabilities, especially that negative. Probability cannot be negative. Now, granted that you have a properly made discrete probability distribution, you can find the mean of that discrete random variable using this formula. So the mean of a discrete random variable x is given by the sum of x times p of x. So remember your order of operations, you do the multiplication first and then you do addition. So basically what you do to find the mean of a discrete random variable is you multiply each possible value of x together with its corresponding probability. As a fraction or decimal, do not multiply any percents. So you're going to multiply each outcome of x together with its corresponding probability. Then you're going to take all of those products and add them together. So this is the this is the discrete probability distribution that we just made for the number of sales for that employee. And what we're going to do is we're going to find the mean of this discrete probability distribution. We're going to find the mean of that discrete random variable and we're going to interpret it. So the first thing that I'm going to do is I'm going to multiply together x times p of x. So I'm going to multiply 1 times 0.16, which does give us 0.16. Then I'm going to multiply 2 times 0.22, which gives us 0.44. Then multiply 3 times 0.28, which gives us 0.84. Then I'm going to multiply together 4 times 0.20, which is 0.80. Then we're going to multiply 5 times 0.14, which is 0.70. Then we are going to take all of these products and we are going to add them all together. So the sum of each x times p of x is going to equal 2.9. So 2.9 here is going to be the mean of our discrete random variable. So interpreting this in context, what this means is that on average, this person made approximately 2.9 sales per day. So this is the mean of that discrete random variable x. Now, for standard deviation of a discrete probability distribution, unfortunately, you're not going to be doing this on a calculator. We are going to be doing this formula by hand. So this is the formula for the standard deviation of a discrete random variable. Now, with this formula, as scary as it looks, you do have to remember order of operations. So we're just going to go through what you should be doing and in what order. In order of operations, parentheses always come first. So the first thing that you're going to do is you're going to take the random variable x. You're going to take each outcome of x and you're going to subtract the mean of the probability distribution. And you're going to do that for each individual value of x. And since that's in parentheses, you do that subtraction first. Then, after you do that subtraction, after parentheses comes exponents. So you're going to square them next. So you're going to do the squaring. So you're going to do that x minus mu squared. So each of those differences, you're going to then square them all. Please use parentheses. Then, after exponents comes multiplication / division. So next, you're going to multiply them all by p of x. Then after multiplication comes addition. So then you're going to, by this symbol, add them all together. And then after you do the adding, the last thing that you should do is you should take the square root. Since everything here, this entire formula was underneath the square root, you do need to do all of that first before any square rooting happens. So after you add them all together, the last thing you do is you take the square root, and then that will be it. So we're going to take that same same probability distribution, and we're going to find the standard deviation of this discrete random variable. So from the last example, we did get the mean to be 2.9. So we're going to be using the mean of 2.9 for each of these. So we are going to just keep in mind this formula and this order of operations. So the first thing that we're going to do is for each individual outcome of the random variable x is we are going to take that outcome and subtract the mean. So we're going to be subtracting 2.9 from each of these outcomes of x. So 1 minus 2.9 is negative 1.9. 2 minus 2.9 is negative 0.9. 3 minus 2.9 is 0.01. 4 minus 2.9 is 1.1. And then 5 minus 2.9 is 2.1. Keep in mind it is x minus mu, so please make sure that you're doing these subtractions in order. After the parentheses comes exponents. You're going to take all of those differences and then you're going to square them all. Now remember, when you are squaring negatives on a graphing calculator, first of all, you do need to make sure that you are using the negative button. So most graphing calculators have a negative button that is different than the subtraction button. The button that you will use for negatives is near the decimal point. Also, if you are squaring a negative, you absolutely need to use parentheses. So you should type parentheses 1.9 and then close the parentheses and then hit the squared button. So, for example, for this first one, if you do parentheses negative 1.9 parentheses squared, you should get 3.61. If you get error syntax, that means that you accidentally used the subtraction button instead of the negative button. So make sure you use the correct button. If you get a negative, that means you didn't use parentheses. You're going to do the same thing for this next one. So you're going to make sure that this is in parentheses before you square it. So parentheses negative 0.9 parentheses squared should give you 0.81. Parentheses are not as big a deal for the positives, although it doesn't hurt. So 0.1 squared is 0.01. 1.1 squared is 1.21. And then 2.1 squared is 4.41. Then after exponents comes multiplication. So you're going to multiply all of those squares by p of x. So you're going to multiply each of these squared values by their corresponding p of x. So 0.16 times 3.61. So we're going to do x minus mu squared times p of x. So 0.16 times 3.61 is going to be 0.5776. And yes, I'm going to write all those down because, again, we need to make sure that we're keeping as much accuracy as possible. Then 0.22 times 0.81 gives us 0.1782. Then 0.28 times 0.01 is going to give us 0.0028. 0.20 times 1.21 will give us 0.242. Sorry about that. And then 0.14 times 4.41 will give us 0.6174. Then after the multiplying comes addition, so then you're going to add them all together. So then we're going to take all of these and then we are going to add them together. So their sum is going to equal 1.618. Then finally, remember this is variance right now. To find standard deviation, you simply take the square root of variance. So then we're going to finally take the square root of that number. So then the standard deviation, sigma, is going to be approximately 1.27. So 1.27 days will be the standard deviation for this discrete random variable x. And then the last thing that we're going to be doing in this section is an application of the mean of a discrete probability distribution. So the mean of a random variable also represents what you would expect to happen if that probability experiment were to happen over thousands of trials. So this is called expected value. Expected value is the value that one would expect a random variable to obtain from a distribution over thousands of trials. So in application, if you were to record that person's sales over thousands of days, the mean of that discrete probability distribution would be what you would expect the number of sales to be on any given day. So the expected value of a discrete random variable is the same as the mean of that random variable, which we can give by the formula E of x equals the sum of x times P of x. Now, especially in the context of money, expected value can be negative. That just means that over thousands of trials, you would expect this random variable to take on a negative value. So here's an example of an expected value question. You will have expected value questions on your homework, and you will have expected value questions on your next exam. I will guarantee at least one expected value question on your second exam. So let's say that at a raffle, 1,500 total tickets are sold for $2 each. So each ticket costs $2. And there are 4 prizes: a $500 prize, $250, $150, and $75. You buy one single ticket, and we're going to find the expected value gain or loss. So basically, we're going to find how much would you be expected to make or lose if off of this raffle if you buy just one ticket. Now, I will say, yes, there is a chance that you could win. Great, but this is, again, over expected. So of these 1,500 tickets, how much on average is each ticket going to gain or lose? So we first need to figure out all of the possible outcomes of our random variable. So our random variable will be the amount that you either win or lose. So we're going to list all of the possible values of x first. Now remember, the tickets cost $2 and you don't get that $2 back. So let's say that you buy one ticket and you are very lucky and you win the $500 prize. How much money are you actually taking home? So yes, you just won $500, but you never got those $2 that you spent on the ticket back. So overall, you are going to only be taking home $498 because you never got those $2 back. Now, if you win the $250 prize, the same thing. You never got those $2 back, so you're actually just going to take home $248. If you win the $150 prize, you're going to be taking home $148. And if you win the $75 prize, you're going to be taking home $73. Now remember, those are just the possible outcomes if you win. What is another outcome of this raffle? The other outcome is that you lose. You don't win anything. So if you don't win one of the prizes, the amount of money is actually going to be -2, indicating that you lost those $2 and then that was it. Next thing that we're going to do is we are going to find each of these probabilities. We're going to find the probability of obtaining each of these prizes. So there is only one $500 prize out of 1,500 tickets. So the odds of winning that $498 is 1 out of 1,500. There's only one $250 prize, so only one ticket out of 1,500 is going to get 248. One ticket out of 1,500 is going to get $148. One ticket out of 1,500 is going to take home $73. And then after all 4 prizes have been claimed, how many losing tickets are there out of 1,500? Well, out of the 1,500, there were 4 winning tickets and 1,496 losing tickets. So the probability of losing $2 is 1,496 out of 1,500. So the expected value, which is also known as the mean of this random variable, is going to be each individual outcome multiplied by its corresponding probability. So the expected value for this raffle will be that $498 prize times the probability of winning, which is 1 out of 1,500, plus $248 times the probability of winning that, which is 1 out of 1,500, plus the $148 prize times its probability of winning 1 out of 1,500, plus the $73 prize times its probability 1 out of 1,500, then plus the other outcome, which is losing that $2, times the probability of losing, which is 1,496 out of 1,500. And as long as you're careful, you can enter all of this into a graphing calculator all at once, and you should get an expected value of approximately -1.35. Yes, it does come out negative, and there's a reason. So what this means is that over these 1,500 trials, each individual ticket is expected to lose $1.35. So if you were to buy exactly one ticket, you are expected to lose $1.35. Now, granted, there are some people who are going to get lucky. This expected value isn't looking at that. Expected value is looking at what is happening on average. On average, everyone is losing $1.35. Even if some people get lucky, on average, everyone is expected to lose. So for this next one, a roulette wheel, which is a great application of expected value. A roulette wheel has 38 probable outcomes, and you can sort of see from the picture here that each of the squares is a different. Each of the squares has a color, and each of the squares has a unique number. 18 of those squares are black, 18 of those squares are red, and 2 of them are green. And each of them has a unique number associated with them, so those are what are called particular outcomes. So, this 21 right here is considered a particular outcome. And while roulette wheels can be really complicated and the betting can be really complicated, we're going to look at 2 really simple bets. So you can bet $1 on a particular outcome. So if you bet $1 on a particular outcome, the winner gets that $1 back plus an additional $35. And then if they lose, they don't get that dollar back, and then that's the end of it. Another type of bet is a $1 bet on a black or red slot. If they win, the winner gets that $1 back plus an additional dollar. And if they lose the dollar, and then that's it. And what we're going to do is we're going to find the expected gain or loss of each bet. So for this first one, we're going to bet $1 on a particular outcome. So a dollar bet on a particular outcome would be an example. I bet that the ball is going to land on red 21. So if you were to win and the ball does land on red 21, you get the $1 back plus an additional 35. So you spend $1, which means you're currently at -1. Then you get the dollar back, which puts you at 0. Then you get an additional $35. So if you were to win, the overall take home is going to be $35. So that's one outcome of this random variable x, is taking home $35. Then we're going to multiply it by the probability of winning. Now there is only one square that's red 21, so 1 out of 38 squares is your winning square. So $35 times 1 out of 38, which is the probability of winning. Then we're going to add to it the other possible outcome. So if the ball does not land on red 21, you lose. So if you lose, you're losing $1, which I'm going to represent as -1. You don't get your dollar back. It's gone. That's the end of it. So this is the other possible outcome of your random variable. Then we're going to multiply it by the probability of losing. So if, again, there's only one square that has red 21, there are going to be 37 other squares that are not the square you bet on. So 37 out of 38 is the probability of losing. So this is the probability of winning. This is the probability of losing. So then when you do 35 times 1 over 38 plus -1 times 37 over 38, you're going to get approximately -0.053. So in context, because expected value is negative, you are expected to lose about 5 cents. Now again, could you get lucky and win the $35 and walk away? Absolutely. But expected value is not looking at what could happen for one individual person. You could just get really lucky, know to walk away, and you got $35. Fantastic. Expected value is what happens over thousands of trials. So over thousands of trials, winners, losers, people who walk away, all put together, everyone on average is expected to lose 5 cents for each bet. So for number 2, we're going to place a $1 bet on a black or red slot, and we're going to figure out its expected value. So if you place that $1 bet and I say, I'm going to bet that the ball is going to land on a red slot. If the ball does land on the red slot, you get that $1 back plus $1. So overall, you are taking home an additional $1 because you spent $1, got it back, which gave you put you back to 0, and then you got an additional $1. So one probable outcome is $1 times the probability of winning. Now, if you bet $1 on a black or red slot, there's 18 of each of them. So regardless of whether you bet black or red, there's 18 of those particular color that you bet on out of 38. So 18 out of 38 is the probability of winning that bet. Then we're going to add to it the other outcome. So the other outcome, okay, I bet the ball's going to land on a red slot and it doesn't land on a red slot. That means you've lost your $1. So -1 is the other possible outcome. And then we're going to multiply it by the probability of losing. So you're going to choose a color, black or red. There's only 18 of them, which means 18 of them are the other color, plus there's 2 green spots. So in total, there are 20 other squares that are not your color out of 38. So then when you do all of this adding, multiplying and adding, you're going to once again get -0.053. It's no accident that this came out the exact same. This means that, again, on average, over thousands of trials, each individual bet is expected to lose 5 cents. Over thousands of trials, so the house always wins, even if some people get lucky. So that's not going to be it for probability distributions. In the next section, we're going to be looking at a very specific type of discrete probability distribution called a binomial distribution. So thank you all very much for watching, and I will see you in the next video for more on discrete probability distributions. Bye-bye.